Alright, in this video we're going to be looking at section 2.5. We're going to be looking at equations of lines and planes in space. So this is going to be the first of two videos. So we're going to look at defining a line in space. Okay. So for a given line L in space traveling through the point P, x1, y1, z1, and parallel to the vector v equals, and then the vector ABC. Okay, so let's go ahead and draw that. So there's my point P, and then we'll say that that's our direction vector V, and V will go, and we'll translate it down onto our line, and also line up with our line. So there's our line there, okay, line L. Okay, the vector V is called the direction vector for the line L, and ABC are called the direction numbers. Line L consists of all points Q, X, Y, Z, such that PQ is parallel to V. So, the vector PQ is equal to TV for some scalar T. Normally we would use C, but C is going to be occupied a little bit later. Okay, so let's go ahead and draw that. So there's two different Q's on our line L up there. Okay. Now PQ is equal to, so we put it in the component form, that's going to be x minus x1, y minus y1, and z minus z1. And since it's parallel to vector v, then that's going to be equal to at, comma bt, comma ct. And so then the like components are equal. So x minus x1 is equal to at, y minus y1 is equal to bt, and z minus z1 is equal to ct. Okay. Now we can solve each one of these for x, y, and z, and that gives us the set of parametric equations: x equals x1 plus at, y equals y1 plus bt, z equals z1 plus ct, as a way of defining the line and generating points on the line. If a, b, and c are not 0, then we can also have the symmetric equations if we solve for t. So if we solve for t, then t would be equal to x minus x1 over a. It'd also be equal to y minus y1 over b, and it'd also be equal to z minus z1 all over c. Okay. Alright, so let's go ahead and do an example here. So we're going to find the set of parametric equations and the symmetric equation, if possible, for the line that travels through the point 0, 4, 3, which we'll label P, and the point -1, 2, and 5, which we'll label Q. Okay, so in order to come up with the equation of a line, we need a point and then a direction vector. So we have 2 points. It doesn't matter which one we use. We'll use one of the points, and then we need a direction vector. So what we're going to do is we're going to find the vector PQ, and that's going to be act as our direction vector. So we're going to put it in component form. So -1 minus 0, 2 minus 4, and 5 minus 3. So our direction vector is going to be -1, -2, and 2. Okay, so that's our direction vector. Okay. So now we can form our parametric equation. Okay, so x is going to be equal to x1. So you can either use point P or point Q for your x1, y1, z1. It doesn't matter. I'm going to use point P, so the x1 would be 0. So 0, and then the direction vector, this would be your A, B, and C. So x would be 0 minus t. Y would be 4 minus 2t. And z would be equal to 3 plus 2t. So that's your parametric equations. Or you could use your x1, y1, and z1 as -1, 2, and 5. So x would be equal to -1 minus t. Y would be equal to 2 minus 2t. And z is going to be equal to 5 plus 2t. And so both of those will generate the same line different t values will give you different values on the line, but they will generate the same line. Okay, since our ABC, our direction vector, none of the components are 0, we can go ahead and write them in the symmetric equations. So we'll do the first one. We'll write the symmetric equations. So we'd solve for t in each one. And so we would divide, we would subtract 0 and then divide by -1 for the first one. The second one we would subtract 4 and divide by -2. And then the third one we would subtract 3 and then divide by 2. And there's your set of symmetric equations for the first parameterization. Or we could solve for t again, and we'd have x plus 1 over -1 equals y minus 2 over -2 equals z minus 5 over 2. And of course you can reduce if you can, but those are your symmetric equations there. Okay, we can also write it as a vector value function, which we'll sneak ahead right now. We'll get into that more in chapter 3, but we can write it as a vector value function, and you can write it as -t, 4 minus 2t, and 3 plus 2t. So that would be one way of writing this as a vector value function. You could also use the other set of parametric equations, and so that would be -1 minus t, 2 minus 2t, and 5 plus 2t. And so that would be another vector valued function there. Okay. So we're going to go ahead and look at another example here. We'll look at example number 2. And it says, find the set of parametric equations of the line that travels through the points -4, 5, 2, and we want this to be parallel to both the xy plane and the yz plane. So let's do a little bit of a sketch here, and we'll draw our coordinate system. So we want to be parallel with the xy plane and also parallel with the yz plane. So a vector that would do that for us would be the vector, something simple, the vector j would do that. So vector j is 0, 1, 0. So that'll be our direction vector. And then we got our point, so we're good to go. We got our point and our direction vector, so we can write the equation of the line that is parallel to the xy plane and the yz plane and travels through the point at -4, 5, 2. Okay. So our direction vector would be, I'm sorry, not a direction vector, our set of parametric equations would be x is equal to -4 plus 0t, y equals 5 plus a t or 1t, and z is equal to 2 plus 0t. So x would be -4, y would be 5 plus t, and z would be equal to 2. Now the a and the c in our direction vector are both 0, so we cannot have symmetric equations here. But if we can sneak in a vector value function here, so the vector value function would be -4, 5 plus t, and 2. Okay. All right, so that's how a line is defined in space using vectors, and how to find equations of lines given certain information. Now we're going to look at planes. Okay. So defining a plane in space, given a plane containing the point P, x1, y1, z1, and having a non-zero normal vector, ABC, the plane is the set of all points Q, x, y, z, for which the vector PQ is orthogonal to n. Okay, so let's draw a picture of our plane. So here's our plane, okay, containing the point P and normal vector n. Okay, the plane is going to consist of all points for which PQ is orthogonal to n. Okay. All right. So we could have a Q there. We could have a Q there. We can even have a Q over here. So all those points are going to generate this plane. All right, so PQ, what is it going to look like? We're going to put it in its component form. So it's going to be x minus x1, comma y minus y1, comma z minus z1. And we're going to set this up so that it is perpendicular or orthogonal to the normal vector. So if you remember, if two vectors are orthogonal or normal, that means their dot product is equal to 0. So if we do the dot product of p, q, and n, that's going to be equal to 0. Okay, so we have x minus x1 times a, which would be ax times, it'd be a times the quantity x minus x1. Y minus y1 times b gives you plus b times the quantity y minus 1. And then z minus z1 times c gives you a plus c times the quantity z minus z1. And then that's going to be your standard form for an equation of a plane through x1, y1, z1 with normal vector a, b, c. So in order to come up with the equation of a plane, we're going to need a normal vector and we're going to need a point. Once we have those two things, we're good to go. We can write the equation of the plane. Okay, so we're going to look at two examples here. Example number 3, we're going to find an equation of the plane passing through the point 0, negative 1, 4 and perpendicular to n equals k. So n equals k is going to be our normal vector here. So normal vector is k, which would be 0, 0, 1. Okay, and then this is our x1, y1, z1. We got our ABC. It's going to be 0 times x minus 0 plus 0 times y plus 1, and 1 times z minus 4. That's equal to 0. And so z equals 4 is going to be our plane here. Now I think example 3 maybe doesn't have the best wording. I think what the intent of the problem is, it's the normal vector is n equals k, not perpendicular to n equals k. So we'll say the normal vector is n equals k, I think would be more appropriate. That's the intent of the problem here. Okay, example number 4. We're going to find the equation of the plane through the 3 points, 3, negative 1, 2, 2, 1, 5, and 1, minus 2, minus 2. So what we want to do is, let's say we got our 3 points, and so we're going to make a vector here, and we're going to make a vector here. And then, if you remember, the cross product of those two vectors will produce a normal vector. And that's what we're going to do here. So we're going to find two vectors, and those vectors will ensure that all 3 of those points are considered here. And then we'll take the cross product, and that'll produce our normal vector. Okay, so let's go ahead and do that. So we'll label these points P, Q, and R. And we'll find PQ. Okay. So I'm going to put it in component form. So it's going to be negative 1, 2, and 3. PR. I'm going to put that in component form as well. So it's going to be negative 2, negative 1, and negative 4. And so our normal vector that we're going to use is going to be the cross product of PQ and PR. And if you recall, the cross product of two vectors, that is a vector that's going to be normal or orthogonal to the two given vectors. IJK, negative 1, 2, 3, negative 2, 1, and negative 4. Okay, so the I component, 2 times negative 4 is negative 8, minus negative 1 times 3 is negative 3. Okay, then remember the J component is negative. And we got negative 1 times negative 4, which is 4, minus negative 2 times 3, so minus a negative 6, comma, and then the k component, -1 times -1 is 1, and then minus -2 times 2, which would be a minus a -4. So then our normal vector is going to be -5, -10, and 5. Okay, now there is nothing wrong with using this. This is a normal vector. It doesn't have to be the only exclusive one, but we can scale this down. So what we're going to do is we're going to multiply this vector by 1/5, and so that would still be a parallel vector, so it's going to be going in the same direction. It's still going to be a normal vector to both PQ and PR, but now we have smaller numbers. So we're going to scale that down. So now the normal vector we're going to use is -1, -2, and 1. Okay, so it's going to be -1, and then I can use PQ or R. It doesn't matter which one. I would probably use the one with the smaller numbers, I suppose, or if some of the coordinates are 0. I'm going to go ahead and use P because it's the first one. I mean, they're all going to give you the same equation. They will look different, but it's the same equation. All right, so we got -1, x minus 3, minus 2, y plus 1. There's a common mistake that I see on my Open Math is accidentally putting an x there instead of a y. Okay, and then plus 1, z minus 2, and that's going to be equal to 0. Okay, and so that is the equation of the plane through 3 points. Whenever you have a problem like this, it's always the same way. Find a PQ, find a PR, find their cross product that produces your normal vector. You got your normal vector, and then use one of the 3 points. Doesn't matter which one, but I would use the smaller numbers. Okay. All right, so this video is going to probably be a little on the longer side here. I got a couple more examples to look at here, so we're going to go ahead and look at it. Problem number 5. I'm going to find the equation of the plane that passes through 3, 2, 1 and 3, 1, -5 and is perpendicular to the plane 6x plus 7y plus 2z is equal to 10. And this is going to use the fact that if the normal vectors of two planes are normal, then the planes are normal to one another. And I'll try to draw a sketch. So we have normal 1 vector, and then normal 2 vector meeting at a 90-degree angle. So here would be one of our planes and our other plane. And so they're going to be normal to one another. Okay. So we're going to go ahead and find vector PQ. So we'll label 3, 2, 1 as P, 3, 1, -5 as Q. So vector PQ is going to be 3 minus 3, 1 minus 2, -5 minus 1. So vector PQ will be 0, -1, and -6. And we want it to be perpendicular to the plane that's given. The vector there is, the normal vector of it is 6, 7, and 2. So that's the nice thing about the plane here. Well, it's not quite standard form, but whatever the coefficients on the x, y, and z are, those are going to be the values of your ABC and your normal vector. Okay. All right. So the plane that we're going to construct, we want it to be normal to PQ, so that'll ensure that P and Q are on the plane, and we want it to be perpendicular to the plane that's given, so we want it to be perpendicular to vector N. So I have 2 vectors, and I want another vector that's perpendicular to those 2 vectors. I'm going to find the cross product. So PQ cross N, IJK. So 0, -1, -6. 6, 7, and 2. -1 times 2 is -2. Minus 7 times -6. It's going to be -42. Remember, the J component is the opposite sign. So we got 0 times 2, which is 0. Minus 6 times -6, which would be -36. And then the k component, 0 times 7 is 0, minus 6 times -1, which would be minus a -6. So that's going to simplify down to 40, -6, and I'm sorry, -36 and 6. Okay, this is the normal vector that we're going to use for the plane that we're making. The numbers are a little bit larger. I do see I have a greatest common factor of, it looks like probably 2. So I'm going to scale that down a little bit. So for our normal vector, we're going to use half of this one. So we're going to scale it down, so half of this vector here. So that vector is going to be 20, -18, and 3. Okay, so then now I'm just going to use one of my points, 3, 2, 1, or 3, 1, -5. I'm going to use 3, 2, 1. So it's going to be 20 times x minus 3 minus 18 y minus 2 plus 3 z minus 1, and that's going to be equal to 0. Okay, and so we did use this fact here. If the normal vectors of two planes are normal, then the planes are going to be normal or perpendicular or orthogonal to one another. So that means they intersect at a 90-degree angle. Okay. Got a few more to go, so hang in there. We're going to be looking at finding the angle between two intersecting planes. Okay, so finding the angle between two intersecting planes. For intersecting planes, p sub 1 and p sub 2, with normal vectors n sub 1 and n sub 2, the angle theta is going to be between 0 and pi over 2, so it's going to be most likely an acute angle. Maybe it'll be they meet at a 90-degree angle if they're orthogonal. So the angle theta between 0 and pi over 2 between the two normal vectors is the same as the angle between the two planes. So we're going to find the angle between the two normal vectors. That's going to be equal to the angle between the two planes. But we want the acute angle. So we're going to use the formula cosine of theta is equal to u dot v over the magnitude of u magnitude of v. So this was how we found the angle between two vectors earlier on. And the only difference here is we're using the normal vectors, and then the absolute value ensures that the angle that the cosine inverse function gives us is between 0 and pi over 2, which would be in quadrant 1. Okay. So I'll make a note. Absolute value only used for angle between two intersecting planes. So the intersecting planes will have both a larger angle and the smaller angle, depending on which side you're looking at. So we want the smaller one. If n1 and n2, they're dot product, so the dot product of n1 and n2 is equal to 0, then the two planes are perpendicular. If n1 is equal to c n2 for some scalar c, then the two planes are parallel, and so then we want to be asking this question about the angle between the two intersecting planes. All right, so let's go ahead and do an example here. So we're going to find the angle between these two planes. 3x plus 2y minus z is 7, and x minus 4y plus 2z is equal to 0. So the first normal vector is going to be 3, 2, and -1. And the second normal vector will be 1, -4, and 2. So we need the magnitude of n1, which is going to be, I believe, the square root of -14. And the magnitude of the second normal vector, we'll go ahead and find that as well. I think it's going to be square root of 21. Okay. And then we also need the dot product, the absolute value of the dot product of the two normal vectors. So absolute value of 3 times 1 plus 2 times -4 plus -1 times 2. And so that's going to be the absolute value of 3 minus 8 minus 2. It's going to be absolute value of negative 7, which is 7. Okay. Now theta is going to be equal to the cosine inverse of the absolute value of the dot product of the normal vectors divided by the magnitude of each one of those normal vectors. So this is going to be equal to the cosine inverse of 7 over the square root of 14 times the square root of 21. And punch that into your calculator, but don't punch too hard. It's going to be about 65.91 degrees is going to be the angle between those two vectors. Okay. Alrighty, I got 2 more examples. This should be a little bit shorter, so hopefully we're done about the 30-minute mark here. So let's knock them out. All right, example number 7. Find the line of intersection between the planes 3x plus 2y minus z equals 7 and x minus 4y plus 2z is equal to 0. So we're going to set it up as a system of equations. So probably in like algebra 1, maybe algebra 2, you solve systems of equations. This would be, if we were to solve and find a point of intersection, that'd be solving a system of 3 equations and 3 unknowns. This is a system of 2 equations and 3 unknowns. So we're not going to have a point of intersection. We're going to have most likely a line of intersection. But we're going to solve it kind of similar to how you would solve by the elimination method. So we're going to eliminate one of the variables. Now this one is particularly nice. Notice that if we multiply the top equation by 2, not only will the y's cancel, but also the z's will cancel. So that's particularly nice here. So we're going to multiply top equation by 2. So that gives us 6x plus 4y minus 2z. And don't forget to multiply the 7 by 2 also. That's a lot of times where the mistake is made. Equals 14. And then the bottom, x minus 4y plus 2z is equal to 0. And then we'll go ahead and add those equations. And so we're going to have 7x, both the y's and the z's absorb. So we have 7x is equal to 14, which implies that x is equal to 2. Okay. Now we're going to plug 2 back into one of the equations, doesn't matter which one. I'm going to plug it into the second equation. Looks a little bit simpler. So 2 is equal to negative 4y plus 2z, and that's going to be equal to 0. Now what we're going to do is we're going to solve for either the the z or the y in terms of the other variable. It really doesn't matter which one. You'll get different parameterizations, so they'll look different, but they actually parameterize the same line. I'm going to solve for z because it's going to be a little bit easier to do. So if we solve for z, we would add 4y and subtract 2. So we'll divide both sides by 2. And so we have z is equal to 2y minus 1. And so we're going to parameterize our line. Okay. Okay, so x is 2, so that's good to go. Now I can either let y equal t or z equal y. It doesn't. Y equal t or z equal t. It doesn't matter. Probably it's going to be easier to let y equal t. Then z would be equal to 2t minus 1 because it was 2y minus 1. Okay, so we have our parameterization. So I'll use the vector value function r of t. The x is 2, the y is t, and the z is going to be 2t minus 1. And that'll generate. And we can also write this as a set of parametric equations. X is 2, y is t, and z is equal to 2t minus 1. So if we use some software like GeoGebra, we could graph this, and this would generate the line of intersection. Well, I was hoping to be done about the 30-minute mark, but it just takes a little bit more than I thought to knock this one out. So we got one more. Thanks for sticking around. Let's do this last one here. So example number 8, we're going to sketch the graph of the plane and find all intercepts of 3x plus 6y plus 2z is equal to 6. I'm going to go ahead and first draw in our coordinate system. Okay. And if we're going to look for the x-intercept, that means that both the y and the z are going to be equal to 0. And so we're looking at 3x is equal to 6. So that means x is equal to 2. And so our x-intercept is 2, 0, 0. So we'll go ahead and plot 2, 0, 0. So there's our first intercept. If we're going to find the y-intercept, that means that both the x and the z are equal to 0. So then we have 6y is equal to 6, which implies that y is equal to 1. And so our y-intercept would be 0, 1, 0. So go ahead and plot that as well. And finally, we'll graph the z-intercept. So first we'll find it. So if we're looking for the z-intercept, that means both the x and the y are equal to 0. So we're going to have 2z is equal to 6. So z is going to be equal to 3. So then our z-intercept would be 0, 0, 3. Okay, so I have my x, y, and z-intercept. So we'll go ahead and connect them. And so we're just going to graph a little bit of the plane there. So this is just what's in the first octant there. So it looks kind of like a triangle. Okay. Alrighty, so we were pretty close to the 30-minute mark. So stay tuned for part 2.